Okay, so last bit about Laplace transforms, delta functions. So define what a delta function is, and then we'll talk about the Laplace transform of the delta function and what it does when you multiply it by functions, and then some examples. So the delta function models a short, sharp impact, right? So this is a little paragraph about physics. What the upshot here is, you can read it obviously, but the upshot here, tablet, mdv equals dp, right? So mass times change in velocity, you can think of that as change in momentum. Force times a small amount of time equals a small amount of momentum. So a force F applied for a very short time dt causes a change dp in momentum. And that's what's called an impulse, right? It's like if you smack something. And the total change in momentum is really the integral of f dt, and that equals the change in p. So we want a 1 unit change in momentum. So delta p equals 1. So we want this integral to be equal to 1. And there's a couple of ways to do that. You can say you start your force at 0 and you end it a very short time later. And so here's the force. The impulse, the change of momentum, is the area underneath that. We want that to be 1. Right? And so you can adjust the force. So if you know the time interval, you can adjust the force so that area is 1. But suppose we want an even smaller time period, then I have to have a much higher force to keep the area equal to 1. And if I let delta t go to 0 in my mind, what I have is an instantaneous force with very high infinite force applied over a very short period of time. So of course, and that's in the limit, the mathematical limit of that. So the delta function then is the limit of the forces as dt goes to 0. This should be an arrow, right? So it isn't really a function, it's actually something called a distribution, because basically, if you define it in this way, what it means is we have a function that's infinite at 0 and 0 everywhere else, but its integral is 1. And that's a little bit weird, but it's the result of this limiting process. So the idea is that if you want to change the momentum of something by 1 unit, you can apply a short, low force over a long period of time, or a very high force over a very short period of time. And that, because the product of force times time is the change in impulse, is the change in momentum. So if you take the limit mathematically, you get something called distribution, and this is its property. When you integrate a function times the delta function, you just get back the value at a. So what's the Laplace transform of the delta function? That's actually really easy to compute. 0 to infinity of Laplace transform of delta a of t equals integral from 0 to infinity of delta a of t e to the minus t a of ts dt. So this is our function. This is our delta function. Inside an integral, what does the delta function do? It just takes your function and it sets t, the thing you're integrating by, equal to a. So it's just that. And note that this is tied to step functions, because the Laplace transform of a step function of use of a of t was e to the minus as over s. So generally when we see, I mean, physically that makes sense, right? If you hit something really sharply at a, give it a sharp impulse, its behavior will change, and so we'll end up with a step function. So here's some examples. Why don't we, the other thing is, what's the Laplace transform of f of t delta a of t, and why do we not actually need that? Well, that becomes the integral from 0 to infinity of f of t e to the minus ts delta a of t dt. And when you integrate with the delta function, all you do is you just plug the a in for t into whatever function you're integrating by. So this just ends up being f of a e to the minus as. This is a constant, so we don't need to worry about it much. Okay, so solve this differential equation. Laplace transform of y equals Laplace transform of the delta function at t, Laplace transform of y prime. So this becomes s Laplace transform of y minus 0, because the initial condition is 0, equals e to the minus s, because a is equal to 1 here. So Laplace transform of y equals e to the minus s e over s. So what is y? Well, this is just the Laplace transform of u1 of t. So we gave something a little shock, and it just moved 1 unit, and it stopped. So the graph of y looks like that. We gave it a 1 unit impulse, and it moved 1 unit, and it stopped there. So y double prime plus 3y. So this again is a mass on a spring. With no friction, and its natural frequency is square root of 3. And what we're doing is we're just giving it a little shot of force at t equals 2, and it's a force of size 5. So to solve this, we get s squared Laplace transform of y minus s, and that comes from the initial condition, plus 3 Laplace transform of y minus 3, and that also comes from the initial condition. Oh, no, I don't have that because this is y, not y double prime. Sorry about that. Equals 5 e to the minus 2s. So we get s squared plus 3 Laplace transform of y equals s plus 5 e to the minus 2s, or Laplace transform of y is equal to s over s squared plus 3 plus 5 e to the minus 2s over s squared plus 3. Now recognize this term, s over s squared plus 3, this is a cosine term. This is a constant over s squared plus 3, so this is going to be a sine term, and to have a sine term, I have to have the correct constant in the top. So we will write this as 5 over square root of 3 times square root of 3 over s squared plus 3, and there's my sine term, e to the minus 2s. Great. So what is y equal to? S over s squared plus 3 is cosine square root of 3 of t. And then we have, this is a sine term with a coefficient out front. And then the e to the minus 2s, that means we have a step function, u sub 2 of t. So we want u sub 2 of t sine of root 3. And every time you have that step function, you have to shift your t. Great. So this is the natural behavior of the spring, right? You pulled it 1 unit, you let it go, it starts oscillating with cosine root 3 of t. And then at time t equals 2, you hit it, and it starts moving with this response to the shock that you gave it. And the sum is the motion of the spring. So here's another differential equation. So this is a mass in a spring with, this is underdamped. If you tried to solve this, you would get complex numbers. If you tried to solve it without that. And so we're going to give it a shock at t equals 2 and then impose a force of 1 at t equals 4. So Laplace transform of y double prime plus 2 Laplace transform of y prime plus 5 Laplace transform of y equals Laplace transform of delta 2 of t plus Laplace transform of u4 of t. And so we get s squared Laplace transform of y minus 1 for the initial velocity plus 2 s Laplace transform of y, and but y0 is 0, so we don't pick up any s term there, and then 5 Laplace transform of y equals e to the minus 2s plus e to the minus 4s over s, because that's the Laplace transform of u4 of s of t. Great, so we gather our terms, we get s squared plus 2s plus 5 Laplace transform of y equals 1, that's the one from here, plus e to the minus 2s plus e to the minus 4s over s. So this is, so reading this, right, this is the homogeneous equation. And the characteristic equation of the homogeneous equation, this is going to be the natural behavior of the system, of the spring, given that it's got some friction and we gave it initial velocity. This is going to be the response to the forcing function, the impulse at t equals 2, and this will be the response to a constant force of 1 applied at t equals 4. Okay, so Laplace transform of y equals 1 over s squared plus 2s plus 5 plus e to the minus 2s over s squared plus 2s plus 5 plus e to the minus 4s over s squared plus 2s plus 5. This term needs to have a partial fractions done on it to separate it. And so we get Laplace transform of y is, well, also we'll point out here that s squared plus 2s plus 5 equals s squared plus 2s plus 1 plus 4. So I'm completing the square is s plus 1 quantity squared plus 4. So Laplace transform of y, just rewriting this, this is 1 over s plus 1 squared plus 4 plus 1 over s plus 1 squared plus 4 times e to the minus 2s plus, and here's where we get our partial fractions. I can find it on my sheet here. So this is going to break apart into minus 1 over 5 e to the minus 4s over s squared plus 2s plus 5. Oh, times s plus 2. And that's going to be over my s plus 1 squared plus 4. And then plus 1 over 5 e to the minus 4s over s. So there's our partial fractions decomposition and everything set up to do the inverse Laplace transform. So we've got 4 terms. Some of them are pretty simple. We'll start with this one, the first one. 1 over s plus 1 squared plus 4. We recognize this is a constant over something squared plus something else squared. So I'm going to write that as 1/2 2 over s plus 1 squared plus 4. So this is a sine function that's been shifted in t by 1 unit. And so that gives me 1/2 e to the minus t, that's the plus 1, times sine of 2t. And this is the natural reaction of the system. We gave it a little bit of velocity, but there's some friction, and so it oscillates down to 0. The second term is this one. And so e to the minus 2s over s plus 1 squared plus 4. We know that the s plus 1 squared plus 4 gives me this function. I do need to multiply top and bottom by 2. So I'm going to get this function, because I have the same thing here, but I'm going to shift it to the right 2 units. So we'll get 1/2 u sub 2 of t e to the minus t minus 2 sine of 2t minus 2. So there's the response to the first shock. That's the response to the delta function. And then the last 2 terms are this one and this one. We'll take the easier one first, 1/5 e to the minus 4s over s. And that's just 1/5 u4 over t. So part of the response to what's happening is we imposed a force of 1, right, a constant force of 1 at 0, and this is the response of the system to it. And then there's another response, which is involves sines and cosines. So minus 1/5 e to the minus 4s s plus 2 over s plus 1 squared plus 4. We can break that into 2 parts. We have minus 1 over 5 s over s plus 1 squared plus 4. That should be in parentheses. Minus, times e to the minus 4s. Minus 1 over 5, 2 e to the minus 4s over s plus 1 squared plus 4. And so what does that give me? Well, s over s plus 1 squared plus 4, this is going to be a cosine term that's been shifted by an exponential. So we'll get minus 1/5, and it should be e to the minus t cosine 2t, but this is telling me that I've got a unit function, step function at t, at 4, sorry. And then I get e to the minus t minus 4 cosine of 2 t minus 4, right? And the 2 because this is b squared. This term still has my minus 1/5. It's exactly the sine term shifted to the right at t equals, shifted in t. This right gives me an e, it's shifted in s, so that gives me an e to the minus t. But we also have that thing. So it'll be u4 of t e to the minus t minus 4, and it's sine of 2t minus 4. So these 3 terms, this one, and this one, are the response to this one. The force imposed at t equals 4. This term here is the response to the delta function at t equals 2, and the top term is the natural behavior of the system.